Okay, excellent. Good. So formally, hi everyone. I'm Riccardo. I'm a solution architect at AWS. So solution architect, it means that on a daily basis, I help partners and a little bit of customers when they work with their partners to adopt the cloud and improve and modernize, because modernization is my focus area. And within modernization, I have a specialty in containers. And this is why today I am going to talk to you about inference, so a topic related to artificial intelligence, inference specifically, inference workloads on Kubernetes clusters. So I was saying that my job is solution architect. So for myself and for my colleagues to help the partners and customers, what we do is, yes, we provide support and we talk, we provide some guidance, etc., but we also publish blueprints, frameworks, so a lot of code that is published on GitHub repositories. We have a lot of repositories on GitHub. For example, some of this is taken from a number of repositories which are in Terraform. If you're familiar with it, you can have a look. If you don't use Amazon EKS, which is our managed Kubernetes service, then you can hopefully easily anyway look at ways to customize and take the same pattern that I'm going to explain today and maybe apply wherever you have your Kubernetes clusters. A little bit of maybe introduction about AI, because we talk a lot about it, but maybe I think that giving you a glimpse of what I see in my day-to-day experience in relation to the cases that we work on, the problems the customer face, and the project they work on. I thought maybe to share a few examples very quickly. So, and these are examples where I could see some of the technology that I'm going to describe today. Because again, today we are going to talk about Kubernetes, a specific pattern taken from a blueprint which is published, so open source, which is related to inference workloads on EKS, on Kubernetes. These examples that I was referring to are AI. Where do we see AI applied today, and where do we see customers working? Well, there are two kind of that I can see big areas. One is healthcare, and the other is finance, or broadly finance. In the case of healthcare, I see a number of cases related to projects related to supporting the help desks. Supporting the help desks to scale. So typically they are chatbots. Or in healthcare also imaging. So imaging, companies trying to scan images and understand, maybe detect some signals, understand what's going on, etc., etc. In relation to finance, I can see same pattern related to help desks. So trying to minimize the work from help desks and offload that to artificial intelligence bots, typically. But also, I could see a few cases where companies are trying to develop assistance, for example, for the traders, for trading companies, assistants that actually help in forecasting. And forecasting is also another kind of application when it comes to betting companies as well, or companies that work in auctions. So companies, specifically, I'm thinking about a project where a company working in auction is trying to understand how to actually predict prices of pieces of furniture, for example, before actually going on auction. So yeah, just a few cases, typical use cases that I've seen recently personally. Good, so let's start a little bit. So we are going to walk through all of this, which is a little bit, but we will focus on the cluster. So like I said, we are going to talk about the inference workloads on a cluster, on a Kubernetes cluster. And the pattern, so the code that you can find on Terraform GitHub is actually deploying this cluster with some, hopefully, best practices that you can take reference, okay? So first of all, we have a Kubernetes cluster, which is the big rectangle from here to here. And we have two groups of nodes. The one on the left is the, which is deployed first, is a group of nodes which are called regular instances. They are not specific instances. They have nothing. They are VMs, of course. They are, in this case, Amazon EC2 instances specifically, VMs with nothing really special. So their only duty is to provide some sort of bootstrap nodes, a set of bootstrap nodes for our cluster, because in here we deploy these pods, these critical add-ons. A note, if you are not familiar with Amazon EKS, Amazon EKS has the control plane managed. So you don't see any control plane here because this is only the data plane. The control plane is managed by AWS. It's not in your account. You don't manage it. Therefore, this is actually the first set of nodes that are deployed to support the critical pieces, the critical components. And in fact, you can see, for example, the CSI driver, core DNS, etc., etc. I'll focus a little bit on the first one here, which is Carpenter, because Carpenter is our autoscaler, cluster autoscaler. So if you're familiar with the cluster autoscaler, the traditional cluster autoscaler, Carpenter is a little bit different, and it is, again, an open source project. So it's published, okay? So it's available, again, on GitHub. And the purpose of Carpenter is to remove a limitation, let's say, of cluster autoscaler. Because with cluster autoscaler, and we are talking about the autoscaling or the scaling of capacity here. So just to clarify, so whenever we need additional capacity, we need more nodes, we need more VMs, more instances into our data plane, into the cluster, and this is the responsibility of the cluster autoscaler. So the cluster autoscaler typically works on managed node groups. The managed node groups are kind of homogeneous, and this is the limitation in what, in how they are defined from a perspective of CPU and memory. So if you want to use different types of nodes, you need to define different groups of these managed node groups, which are homogeneous again in terms of CPU and memory. So it's a little bit of a burden to manage multiple managed node groups, which are auto-scaling groups into in AWS terminology. So Carpenter tries to address this limitation as a first step. So what it does is it doesn't use any group, it talks directly to the Amazon EC2 Fleet API. In the case of other providers, it's something else. And by the way, Carpenter is also available for other cloud providers. They adopted it and they made the interfaces. So what Carpenter does is it computes. First of all, it looks at the state of the cluster and the pods. So if it sees that there are some pods, when I say pods, and well, up to now, hopefully I'm talking about something that you guys are familiar with, kind of, yeah, okay. So pods are basically the unit of deployment. They contain containers, okay. So within the pod, we find containers, typically one, but can be multiple. And that's the unit of deployment in Kubernetes world. So whenever we want to scale a workload, we typically scale the pods. And I'm saying scaling without saying that we want to scale typically horizontally. We don't want to increase the size of a pod. So we don't want to increase memory and CPU because there is a limit. and we want generally, as a good practice, we want to try and scale horizontally instead of vertically. So we want to increase the number of pods. So let's say that there is an event and we want that makes the number of pods increase, and we will see how that happens. So workload scaling, by the way, it will happen because of horizontal pod autoscaler, but just a second. So the first thing that happens is that we increase the number of pods. So the pods will, if there is capacity, so if we have enough capacity in our data plane, the pod will be scheduled. So the Kubernetes scheduler will take the pod and assign it to a node. And that's the end of it. But if there is no capacity left, the pod will stay in pending state. And this is where Carpenter starts making its changes. So it looks at pods in pending state and makes some calculations. So based on a few parameters that we will see, and it calls this Fleet API, EC2 Fleet API that I mentioned, so talks directly to the cloud, AWS in this case, and requests a specific node or a number of nodes. How it does that is through these custom resources. They are called the node class and node pool. So this is actually the snippets from the definition of these node class and node pool custom resources. So the node class specifies a number of parameters, relatively interesting for us at the moment, but they are the AMI, so the Amazon Machine Image, which is basically including a definition of how the basically the operating system and a few other packages that form the actual image that is provided to the VM to actually start. We have subnets, security groups, and so on. The node pool is where we define some interesting property, like, for example, the instance family. Here it's a G5. We are defining a G5, which is a GPU type of instance, because what we want to create, and you will see later, is another group, which is the one which you can see here on the right. Here you see GPU instances. So in order to create those instances, we are creating a node pool that carries the information to how we wanted these GPUs instances from the cloud. So they need to be GPU instances, and we provide a set of values here. These are the sizes. So the size of an instance, which typically includes CPU, memory, GPUs, number of GPUs, memory of the GPU, and so on. The architecture, in here we have an x86, but we also can have ARM architectures. And here we have the capacity type as well. So we have on demand, which is the typical general type that people use. If you want to save, optimize your costs, you can use spot instances, but this is again an AWS concept. I will not go further on that. If you have questions, maybe later. So this is a definition of a node. So we tell Carpenter how to allocate nodes, how to create nodes, and how to talk to the to AWS or the cloud provider to actually create additional nodes if there are pods in pending state. And we also tell Carpenter that we want nodes, we want to associate these labels and these stains. So we only want GPU workloads to land on these instances, because of course, if you don't need the GPU, there is no need for a pod to land on a GPU instance, technically, and because it costs more generally than a CPU. So we put this taint, which is basically, if you are not familiar with taints, it is basically a way to reject pods that are not that does not have a counterpart, and the counterpart is this one. Tolerations. So this pod, for example, that we will see is a inference workload, and the definition of this pod will have a toleration. So the node will have a taint, the node allocated by Carpenter. Basically the taint says this is a GPU node, don't put anything which is not suitable for a GPU node. And this one is saying is actually on the pod and is saying, okay, I'm fine with that limitation, I can accept it. And the node selector actually is basically telling Kubernetes, I actually want this type of node, and I have a toleration as well. Anyway, let's go back just a second. So we were saying that we have these two custom resources, which are part of Carpenter, and we are telling Carpenter to allocate these nodes in case we want to create GPU workloads. So the GPU workloads that we create in this blueprint are based on Triton, which is exactly this one. So we have these instances, and when the blueprint deploys this pod, it will happen that the pod will go on pending state, and because we have that definition of node class and node pool, Carpenter will see that that the pod is in pending state, and the pod requires and tolerates actually GPUs. So we'll allocate GPUs. Carpenter, to complete the picture, makes computations continuously. So it monitors the cluster and understands if there are pods that could be placed somewhere else. So if nodes are underutilized, makes some calculations, and for example, removes a node, pods will be rescheduled and will go into the other node, or could, for example, remove both nodes and replace them, if it's cheaper, with a single node. Again, Carpenter looks at costs as well, so continuously optimizes costs. The way Carpenter allocates nodes is this one. It works like this, just very briefly. So it creates what is called a node claim, and the node claim represents the request to the cloud for a node. So Carpenter first creates the node claim. The node claim can be in these states, so launched, register, initialized, and ready. Then Carpenter requests to AWS in this case the node. AWS launches the node. In this case, the VM is an EC2, of course. And then once the EC2 VM is launched and running, it's not still yet part of the cluster, so it will be registering itself with the cluster. And then when it is registered, it becomes ready. All this flow can be seen by checking the Carpenter logs, by the way. So you can monitor what's happening. So going back here, what we have is our inference pod. So what does it mean in our case? So in this specific case, I am using Triton server. I'm assuming you don't know Triton. It's also an open source project. It runs on NVIDIA GPUs, so it's very specific, but it's also supporting other types of architectures. It also can run on ARM, for example. So what Triton is an inference server. Okay, so I'll move here to explain a little bit the features. So whenever you have a model, you need to run the model, and you need to be able to, because the model by itself is kind of a structure. You need to use the model and run it, okay? So you need a runtime. And you need also something that receives requests, takes the model, run the model with the request, and then returns a reply. This is what is the duty of Triton, of the Triton inference server. So the way it works is that Triton can have multiple backends. Backends are basically runtimes. For example, in our case, we have a VLLM backend in Triton, but it could also be TensorRT, for example, PyTorch, etc., etc. It can run all of them in parallel as well. So you can have models. Yes?
So I guess each backend is just a different container image you launch running because the main instance is scheduling jobs, right?
No. So a single Triton container can run multiple.
Okay. So it's not launching sub-processes, like anything like jobs.
So internally can have whatever processes it needs.
But it's just one container.
But it is one container. Okay. And actually, you can play a little bit with it, because you can have, for example, a Triton pod definition that if you have multiple GPU instances, you can decide, well, I have one instance with multiple GPUs. I might want to assign, let's say I have 4, I want maybe 4 pod instances of Triton, or I want just one that manages all of them. And you can do that. There is later a little snippet about that. So the way it works, again, looking at the flow of the requests within the inference server, is that you have inference requests, HTTP requests. They come in, and we have, depending on the models that we have running, we can have one instance of the model or multiple instances of the same model. So if you want to run multiple instances within Triton, within the inference server for the same model, is because you want to run requests in parallel. So they come in, they have one queue per model type, per model, And each model can be replicated multiple times within Triton. To be able, for example, you have inference requests to, for example, we have one model here and another model here. Maybe I want to run multiple requests for the same model, then I can increase the number of instances of the same model within Triton. And up to here, they get into the backend, which I was telling you about. So the flow is, I receive the requests, I have my backends, all running within Inference, the Triton Inference server, and then I pass the requests to the right model. One or multiple instances of the same model, depending on the configuration that we will see in a second.
Can you run different kind of records? Or just one?
Yeah.
Ah.
Yes. So then what happens is that these backends, as a general activity of what they do, not specific really to Triton, they translate the request and the model into some tasks for the GPU. And these series of tasks are called the CUDA streams. So CUDA streams are sequence of tasks that need to be executed serially. So they cannot be executed in parallel in relation to one single model, okay? So what happens is that out of here, we have CUDA streams. And these are executed, these instructions need to be executed serially. What happens is that when they get to the GPU, the hardware scheduler can actually execute them in parallel. And this is the optimization that is put in place by Triton. So you don't need to basically wait. So if in here you are not fully utilizing the GPU, you can add it adds multiple streams, and it is the hardware scheduler then that takes all these streams and merge them together in order to optimize the usage of the GPU. Other ways to actually utilize concurrency on GPUs, if you've seen them, you can use two of them, which is time slicing and multi-instance GPU, or MIG for short. With time slicing, it works exactly like on CPUs. So you take, with a scheduler, so you divide the time in slots, and you assign the workload. It's not related to Triton. Triton uses this logic, okay? It's not related to this, but you can divide the time of the GPU into different and assign those slots to different inference workloads. Okay, so and you can do that kind of indefinitely. You can use a lot of them. With the multi-instance GPU, you have actually you are dividing the GPU into multiple areas physically, and there is a limit, and it only works with some GPU models which are kind of fairly recent. It doesn't work with the older. So in here you have a limitation. So a limitation in the number of workloads that you can assign to the GPU. But it's good for fault isolation, because actually the GPUs are subdivided into blocks. So each block is independent. Okay, so this is what Triton is. And we have, in fact, our pod here, which, like I said, its history is it's deployed, goes into pending state. Carpenter sees that, and then, based on node class and node pool, allocates a GPU node to host it. Another component that is installed or deployed on on the GPU nodes is the NVIDIA device plugin, basically, which is a daemon set that exposes GPU as a resource to the workloads. So now we have our Triton server deployed here. Yes.
Does the device plugin work for any AMI? In theory, I mean, like for any architecture of AMI, like Order, Rocket, AMD, whatever, it should work.
Yes, yes, yes. In fact, on EKS auto mode, which is, well, obviously specifically to AWS, it's a new, fairly new feature of EKS where we manage a lot of more stuff. We use Bottle Rocket as an AMI.
That's what I'm asking, like just
okay.
to see if it works with Bottle Rocket.
Yeah. Yes. And there is a specific version of Bottle Rocket. It's called a variant, which supports NVIDIA GPUs. Okay, so a few more words on how you configure Triton. So Triton needs to run your models, and how you tell Triton which are the models is by creating a repo. In this case, it's stored on a external persistent layer. It could be local as well, but it's basically a directory with this structure. You have a models, and then within models you have the model name, the version, and then the model itself. And then you have a configuration file, which we'll see in a second. So the model is here, and Triton, when you point Triton to the you provide as a parameter this the location of this model repository, and Triton will go there and basically pull and launch the model. In this specific case, the model is kind of a wrapper, a Python wrapper, that once running, it pulls the actual model from Hugging Face. So the cycle is I launch my pod, the actual image of Triton is pulled from the registry. It starts running and then looks at the model repository, sees the model. Okay, now I need to go, starts running that model, which again is a wrapper in this specific case, and then the wrapper goes out to Hugging Face and pulls the actual model itself. So yes.
Any way to cache the model, let's say, in something more local, just to save cost on networking with VPC endpoints and so on?
Yes, I'll explain a couple of improvements. Yeah, in a minute. So just for your information, the configuration of the configuration file, which is config pb.txt, which is in here, okay, is reported here, and in there you can basically set a number of parameters, like for example, you have batching. Batching is a parameter that tells the inference server you can group a number of requests, wait a little bit, and then process them together. This is because to optimize the usage of the GPU. So you can configure dynamic batching, for example, and giving it, for example, a maximum delay. So you're telling the inference server you can wait up to this amount of time, group together the requests, and then when you have a sufficient number up to this amount of time, you can process them together. But in any case, what other parameters that you can use within the configuration file, and again, there are others, is the number of instances. Instances related to the model instances running within within Triton. So you, for example, you can say within the model instance, you have an instance group, and you can say, for example, I want 1 running on GPU number 0, because maybe your instance have 4 GPUs, okay? And you want also to say, well, I want 2 running on GPU number 1 and number 2. This is a little bit of a detail, but just to explain what kind of parameters you can find in that file. Okay, so now once we have this pod running, it's pulled the model from the repository. From the repository, then it runs the model. The model in this specific case needs to go out again, Hugging Face, and takes the model. Now it's running. Let's have a look a little bit of what's happening when we want to actually drive the scaling. So we talked about scaling with Carpenter, but first of all, before scaling the data plane, we need to have a reason for scaling the data plane. And the reason is I have a larger number of pods. So when do I have an increase in number of pods? When I need it. So we define when I need it by actually, kind of looking at a specific metric that the Triton Inference server exposes as Prometheus metric. So this is the name of the specific parameter, which is called NV Inference Queue Duration Microseconds. It basically says what is the duration, well, what is the time spent for on average for the requests within the queue. If that increases, it means that there is some difficulty. So if I have a large, exactly like with HTTP servers, if I have requests in my queue and the queue grows, it means that my capacity, so in this case, my Triton server, is in difficulty. So we use that parameter here to measure basically how much we want and to drive the scaling of the number of pods. So if that increases, we want to, over a threshold, we want to increase the number of pods. So with a new, for example, pod of Triton server, we will be able, as part of the same service, to actually divert the requests a little bit here, a little bit there, and therefore to separate the load of requests between multiple pods. Typical use case. So we have that metric which is exposed, and as part of our add-ons within the regular node group, so the initial, the bootstrap node group, we have deployed the kubeprometheus stack and the Prometheus adapter. Kubeprometheus stack is basically Prometheus and Grafana and something else. The Prometheus adapter is basically the tool that looks at metrics. We tell Prometheus adapter which metrics we want to look at, and then it exposes them either directly or with some manipulation as part of the API aggregator. The API aggregator is part of the API server. So it basically takes these metrics. In this case, we tell it, look at this source, which is Triton, and we want specifically to look at this one, which is, again, the queue duration microsecond. There is a little bit of a transformation. Doesn't matter very much. It's actually converting that to milliseconds. And we, the adapter takes this metric, okay, which is stored which is actually routed to Prometheus, takes that from Prometheus and export that up to the into the API, Kubernetes API. So at that point, the HPA controller can look at that metric and takes some decision.
How do you connect you said the HPA controller? No?
Sorry.
You said the HPA controller. It's looking at the Prometheus to that metric to make decision to scale horizontally.
It's looking at this, which is an HPA definition.
For Triton, no? That is for Triton exclusively.
This is for that metric. So the Prometheus adapter, very brutally, takes the metric from Prometheus, okay? So the flow is Triton exposes the metric. The metric is taken and put into Prometheus. And then the adapter looks into Prometheus and exposes that as part of the Kubernetes API. And with the HPA, this is a resource which is read by and managed by the HPA controller. It sees that we want to track that metric.
You make a custom metric, so it's HPA, because normally CPU or memory, but you do a
Exactly. Yeah. And then we tell it we want a replica between 1 and 5, depending on that. And that I think is set to something like 10 milliseconds. So if it increases, then we want to increase the number of pods. And let me show you maybe this one, which is a snapshot of what was happening by increasing that metric. So in fact, it's 10 exactly, so 10 milliseconds. So this is the level that we set the boundary in the HPA basically. And in here there are some spikes, 1, 2, and 3 that go beyond that boundary. So the HPA controller sees that they go beyond, so they are above. And what happens is that you can see another 3 spikes here. These are basically the replicas to match what was happening earlier with the metric. Hopefully it's clear. Okay. So now let me explain a couple of additional notes, and this is going back to your question. So all of that pulling from the container image, pull the model, it takes some time. Okay.
Sorry for interrupting. One thing that I didn't understand is the call to the Hugging Face. Okay, why is that happening? Because I am seeing that you are downloading the model, so you have the model locally. So normally when you make a call is to actually use a model remotely. So I'm confused.
No. Yes. Okay. So in this specific case, my model is a wrapper. It's not a real model.
Okay.
It's a Python script. I take the script. There is a Python backend within the Inference server. It starts the Python script,
okay,
and it is the Python script that then takes the model. Yeah. So this one is not really.
It's not a model. It's just.
Yeah.
It contains the SDK, no? Or
it's just a Python script. It just downloads the model and starts running it. So this is not really something that takes time. It's pretty fast. If the model was there, yes, of course. In fact, we actually moved time from here to here. In any case, there is this typically large multi-gigabytes or hundreds of gigabytes stuff, blob, that you need to pull, and that takes time.
That was the question, like average size of the.
Oh yeah, it varies, few gigabytes to hundreds. Yeah. So that takes time because you need, again, to pull the image from the registry, and second, to pull the model. Once the container is running, you need to pull the model. And that is going to take a while. So there are a few improvements that we could put in place if we don't like to wait. So some of them are better than others. So first of all, you can use Sochi, and this is another open source project. So this is a CNCF meetup, so I thought to highlight what is open source. Sochi, which is seekable OCI, it takes a container image, which is made of layers, and looks at the layers that are required before others. And with a specific snapshotter together, the snapshotter is that component that basically rebuilds looks at the layers and then rebuilds the file system image, basically, looking at composing the different layers. So the way it works is it looks at your image and highlights which are the layers that are fundamental to start up the container. If you want to speed up the boot up, then what you do is, with this system, it launches the container as soon as it downloads the first few layers, and then downloads the rest. You don't need to change the image. There is a parallel artifact that is basically a map that you put together with your container, image in the registry. And again, you need a snapshotter. So running in the node, the snapshotter will look at the container image, will look at this map, understands which are the layers that are most important, and downloads those first, and then starts the container before pulling the rest. This improves, but this is related to the container image, not to the model. Same thing, multi-stage builds, if anyone knows what they are. Docker file, you start maybe with a larger image, larger OS, and then you build some stuff, you produce some packages, some libraries, and then maybe you don't need all of that, so you add another from, which might be a smaller OS. The other option, again, and this is container only, the other option is to use the BottleRocket operating system and use the data volume. So BottleRocket, for those of you that are not familiar with, is an operating system. It's based on Linux. It's open source. The main features are that it is minimal. So its only objective is to run a container, nothing else. So, for example, it doesn't have a shell. Everything which could be stripped out, it's been stripped out. So it's very small, and on top of obvious reasons, smaller, less space, it also has a smaller attack surface.
Can you run BottleRocket in other providers?
BottleRocket is open source.
Yes, but you could.
Potentially, yeah. So what so the other features are that it is secure, more secure, or tries to put in place security measures like, for example, the root file system is immutable. So if there are, for some reasons, detection of mutability, it restarts. And there are also controls, checks on whatever is mounted as well. So all the parts related to containers. Okay, so this is a little bit, a few words just on BottleRocket. Why am I talking about BottleRocket? Because BottleRocket has two volumes, one for the operating system and one is for data volume. So containers go, data that goes on the data volume. And what you can do is offline, not as part of your cluster, you can start your EC2 instance or an instance, a VM, running BottleRocket. Launch anything that you want, the container with models as well, and then take a snapshot of the data volume. In this case, we take a snapshot on EBS, the snapshot from EBS, sorry. From EBS, it goes to S3. And then, when you want to launch your instance as part of a cluster, and this is a node class within Carpenter, so you can use a Carpenter node class, and this is useful in this case. You can tell Carpenter in AWS that when the node is launched, the block device maps to an EBS which is taking this snapshot ID here. So it pre-populates the volume with the snapshot we took before. So the container basically is launched with the data already in. Okay, so another option which is not in here, but if you're interested, it's not open source, but it's if you're using GPUs, well, that's kind of a you can find these options paid or free frequently, is to use NIMs. And NIMs, with the NIM operator, cache the model locally. So a NIM is basically a container not related to Triton strictly, but it can run Triton. In any case, they are containers pre-configured by NVIDIA that you can launch on your cluster, and they can cache models locally. You provide typically, for example, an EFS, persistence on EFS in the case of AWS, and the model is cached there. Good. I think I got to the end of it. Yeah, I think that's it.
A question, simple one, about Carpenter. When you define the array of values, for example, the typical case of capacity, yes. Would you recommend to set it like that, like spot and on demand in the same array, or you would recommend to have different node pools with weight? I mean, let's say 80% of the same, exactly same node pool, okay, a copy, but one with capacity time spot and another on demand with different weights. Like I want a weight of 80% for a spot and 20%.
Okay. So for everyone, spot instances are instances that are cheaper, they cost less. The downside is that they are taken from spare capacity within the AWS data centers. So as long as there is this spare capacity, AWS can give them to you at a discount. The downside is that if I need them, I will pull them and give them to someone who needs them and is available to pay at on-demand price. So you need to put in place and be conscious of the fact that, so put in place some mechanism to actually cope with this possible event. And yeah, you need basically to be prepared. I would say that depends on you, on what you want to do.
It's about the same. It's because in the configuration definition that you have,
yeah,
always it will take first
yeah,
spot, okay, and then
no, it's not first.
No, okay, so that's what I wanted to check with you. So
yeah.
It's not first always a spot.
Yeah, no.
Okay. It could be on demand.
It could be on demand.
Even if you have a spot available with that configuration, it will happen that for certain reason, the Carpenter controller detects that an on demand in that case is cheaper than on a spot for certain reason and pick up on demand.
Yeah. There are ways to balance this, but yeah, if you take this as it is, that's what's going to happen. Yes.
So since you mentioned about interruptions, how does this tool deal with those interruptions? I mean, do you have anything in place or do you just retry?
No, it's the duty of the customer. So it's the workload that needs to know that can happen, or anything that you want to put in place to actually cope with it. But there is nothing on the cloud provider AWS side of things, because we're talking about Spot, okay, which is typical AWS terminology and service. There is nothing that will, so you have events that you can listen to, yes, of course, but it's you to act. It's not that.
But Carpenter can listen on an SQS and start a victim, like send you the SIGINs and so on, so that you have 2 minutes.
Yeah. That's going to happen. Yeah.
The tool is gonna do anything, or just no safe, like exit whenever it receives
your workload will be killed.
That's what I'm saying. If this Triton has some kind of graceful shutdown or not?
I don't know.
Okay.
I don't know. I'm assuming that it will be killed. Okay. Good. Yes.
The scaling. How much logic can you put into it? So something like.
How much?
How much logic can you put into it? Is it just simply you can go from this many instances of this type, or can you say once you have enough load, switch from CPU to GPU instances?
Okay. So in this is a pattern, so meaning that we built this kind of logic putting these pieces together. So typically you understood that there are 2 scaling, right? There is the workload scaling, so increase the number of pods, and then pods are not fitting into the data plane anymore, then we need to increase the data plane, right? So that's the capacity scaling. So I'm assuming that you are referring to the workload scaling, so the increasing the number of pods more than the capacity, because the capacity follows the pods being in pending state, right? So in this case, we used two main tools. So one is Prometheus. Prometheus is that metric server that pulls and stores metrics which are exposed by workloads. And we chose to look at those. So depending on the metrics that your workload will expose, you will have them available in Prometheus or not, first of all. Okay, and then we chose to use the Prometheus adapter to drive the horizontal pod autoscaling. The Prometheus adapter is the link between the storage of the metrics and the API that basically makes known to the rest of the Kubernetes world some of the metrics that are in Prometheus in some way. And based on that, we scale the number of pods. What was your doubt?
If you could just tell like in the YAML, okay, from once you get to this latency, because you have a baseline load that's really small, and then you have spikes.
Okay, so this is, like I said, this is one way of doing things. And then another way of scaling horizontally the pods is using other tools. For example, one is KEDA. I don't know if you're familiar with it. It can take other sources of information, even externally to the cluster. For example, you have Amazon SQS somewhere, and you decide that if that queue goes beyond this level, then you will increase the number of pods, even if it is completely unrelated to the cluster. And there is a number of sources of information that can drive the scaling. But that's using another tool, which is, in this case, like I mentioned, KEDA. Again, open source. CNCF. Graduated.
On the architecture, can you tell Carter to use AMD 64 as versions? Can you tell to use x86, 64, V3, V4, or is it just AMD 64 or ARM?
I don't know. I'm fairly transparent. I know you can use the ARM. I think this is the x86 thing identifier. I don't know if you can use further versions, but I think I can find that information quite quickly. Anything else? Oh, yeah.
If I understood correctly, Carpenter is in charge of creating the nodes for the workloads, right?
Yes.
So how would that work with different workloads? You should have a node class and node pool per workload type.
If
for example, what I'm thinking about is, for example, you have a workload that gets the nodes provisioned by Carpenter, and somehow you get also a pod from whatever, a database, a storage, a CNS storage that is not working well with node shutdowns. So how does it work with Carpenter?
you need to define your node classes and node pools per workload if they require different types of nodes. Yeah, in fact, in here we needed GPUs, for example, and you need to play with the placement constraints in order to drive how pods are scheduled on different nodes in order to avoid wasting your resources. Good. Is that it? If it's it, yeah. I have a small favor to ask, which is, as part of our activities when we do talks, we ask for a little feedback. So I have a little survey. It's 2 ratings. So tap, okay? These are mandatory. And then there is a question, which is optional. So if you don't want to tap more on the phone, you can avoid it. And it's just anything that any comment that you want to provide. This is because, again, we are looking at ways to improve the way we do our talks. and for me as well, of course. Tell me if you can do it. Does it work? Ah, okay. No?